Hello everybody, we're going to talk about rates of change and how they relate to functions. Rates of change just say how is a function changing as you change the input value. So it's the change in the function versus the change in the input value. A lot of times you see it as delta y over delta x. Delta is just this triangle symbol. Okay, so example, if you had the point 5, 4, so this is the function, well, actually, let's do it the other way. 4, 5, and -7, 3. Okay, so you had those 2 points. No, yeah, that's right. Okay, so you had those 2 points. You say, well, the change in the function value, it's going from 5 to 3, so 5 minus 3. The difference between those two values, you just subtract and you get 2. And then you also find the difference in the x value. So how does those change? So it went from 4 to -7. So the difference between those two will be 4 minus a -7, which would be a positive 11. So that's how you roughly think about that. It's the change in the y values versus the change in the x values, or the change in the function over the change in the input. So here's an example of, so we have this pattern that's growing, and you can kind of see how the pattern is growing, and even guess what the next one would be, and it would just be 2 more going out like this, filled in. So if we set let's say the function, we want to find out the function of n, and we're going to say it's the perimeter. Let's say it's the perimeter of this shape, just the outside perimeter. Okay, so I can find some values for this. The first perimeter is pretty easy, it's just 4. So we'll call that f of 1. So my input is 1, and I get 4, right? And then the function at step 2, so this is n equals 1, n equals 2, would be, let's see, 3, 6, 7, 8, 9, 10. Right, so 10 is the perimeter there. And then the function at step 3, and we have 5, and 6, 7, 8, 9, 10, 11. So I get 11 to there, and then 12, 13, 14, 15, 16. Right, 16. So we would say the rate of change would be, let's see, the difference in the function values, so 10 minus 4 would be 6 over 2 minus 1, which is 1, so we'll say the rate of change is 6. And now, is the rate of change the same? We'll go to the next step, so 16 minus 10, so the difference in the function values was 6, right? 16 minus 10. And the difference in the inputs was also 1, so it looks like we have a constant rate of change. So if you were to graph this in the plane, we say at point 1 it's 4, and then at point 2 it's 10, so it's 6 more, and then at point 3 it was 6 more. And you would see that when it's growing by the same amount constantly, it's going up by 6 to the next function value, and over by 1, up by 6, and over by 1. You have this sort of straight line, and that's why we give it the name linear, is to say that this is a linear function when it has a constant rate of change. So constant rate of change is linear. Okay, if I were to compare the function, let's say we looked at f of n, and we'll say it's the area instead of the perimeter. Now this would just be an area of 1 square inch, right? So f of 1 is 1. F of 2 would be 4 square inches. F of 3 would be 5 plus 4 is 9. So here the change here the change, so it would be change in the function value would be 3 to 1, and then the next time it's 9 minus 4 would be 5. The change there is 5 to 1. So you see that this is not linear. So we say not linear. And if you were to graph this, you would see that it grows, it starts growing faster. So it kind of curves up. Okay. So this is like an example of something that's not linear. Now, when we look at a table of values, we want to decide, is this a linear function or a not linear function? All we have to do is compare a bunch of points and see if it's constantly going up at the same rate. And this one, let's see, so the change in the y value, so we go -5 minus 2 would be -3. And then 0 minus 4 would be -4, so it grew by 3/4, positive 3/4, because the negatives canceled out. And if I were to graph that, let's just check to see. So 0 in the x direction, -5 would be down here. And the next point is 4, 1, 2, 3, 4, -2. So it looks like it goes up 1, 2, 3, and then it goes over 4. Right, so this is the graphical way to show how it's changing. So it's going up by 3 and over by 4. So this is the change in the function value over the change in the input value. If you want to find what we call the unit rate of change, that is just this fraction. So it changes by 3/4 each time. If this is a linear function, I haven't really shown it yet, but it changes by 3/4. It goes up 3/4 and over 1. So this is called the unit rate of change, or 3/4. A lot of people call it the slope of the line. Okay, let's check a couple more points to see if it is actually changing at a constant rate. So let's compare, I don't know, how about these two negative numbers? So let's try -8 and -4. The difference there would be -4. And then the difference, I have to compare the same way, so -11 to -8. So that'll be, oh wait, this needs to be flipped over, doesn't it? Because I want to compare my function values. They should be on top. So that's a common mistake that a lot of people make. So I'm glad that we're bringing it up now. Is you got to be sure about what you're comparing. So these are my x values and these are my f of x values. So I need to flip that whole fraction over. And if I were to do that, I would get it the right way. So okay, so it looks like, at least when I compare those 2 points and these 2 points, I do have a constant rate of change. So you can compare, maybe pick this point and one of the other ones and see if it is constant throughout. And then you would see that all of those lines, all these points end up on this line somewhere. So -8, -11 is probably way down here, something like that. And it would all of them will line up in a straight line. Okay, so that's what you do. You just find the comparison of the function value versus the input values. Or in the graphic sense, you can think of it as how does it change vertically over how does it change horizontally. And some people call that rise over run. Okay, so there's a lot of different ways to think about it, and there's just a few.